All right, everyone. Good afternoon. Um, so today our goal is to finish our yield stability assignment. Thanks for completing, or sorry, not the assignments, but the exercise. Thanks for completing the assignment. I hope that now that you've read the paper and completed the assignment 7 that was related to the yield stability paper, now we're going to be perhaps some of the things that we were doing in the script of last class are going to make a little bit more sense. And also some of the steps that we're going to use to finish that exercise will also make more sense. All right, so first today we're going to finish that exercise. Then we're going to probably have still time to start a new exercise, which is going to be terrain properties. And then I want to leave some minutes for us to open up if anyone has questions about the midterm, which is this Thursday, right? So in 2 days. All right. So beginning with finishing this exercise, if you want to go to the folder that you have for this course and launching. So we're still within that 07U monitor, right? So that exercise or that project, we really developed a lot of scripts there. So if you want to launch your RStudio project from that folder so we can get started, remember always launch your RStudio instances from the RStudio project and not just by simply clicking on a script to make sure that your paths are all correct. All right, so I believe we stopped, let's see. Right here, right? I think we stopped right here. So as I hope that it is on your side, you should not have anything on your environment right now. If you just open your RStudio project like I did, and so you can come to this chunk here. If you're looking into the tree here or the table of contents, it would be the chunk that says both maps under the spatial temporal stability heading 1. So both maps come to this chunk, and then you can basically hit the play all above or run all chunks above button. And so we're gonna have everything that we did last class being recreated for us. If you did not leave any errors in the code above, then you should have been able to get to this point without problems. And at that point, if you come to this both maps chunk, that's the one that you just clicked the run all above. Now you can actually run this chunk again, just to make sure that you export these two files or these two maps into one file on your output folder. So if you go on output, you should be able to see the SY temp stability PNG, which is this. And although it's not the prettiest looking map at this point, but it was just so we had a version on file for us to look into. So I guess before we get to the next step, I just want to quickly remind you of what we did all the way up until here, just so we get that refresher of where we stopped and what we did and how that's going to follow next. So we basically brought in the wrangled, clean, and interpolated yield maps from 2017, 2019, and 2020, so for 3 years. They all had the same number of observations in each one of them, and we talked about why that was. We then, for each one of those individual years, we calculated the median yield first for that year. And then we calculated the standardized yield, which is basically the yield in any given pixel or cell divided by the median value for that year. We did that for 2017, and then we did a map of it. This is how it looked like. We did it for 2019, and then we mapped it as well. This is how it looked like. And then we did for 2020 individually as well, made a map of it, and then finally combined all three maps. We then interpreted these maps. So if you don't know how to interpret this map, you need to let me know. Because this could be, well, let's see. I think yeah, so until the paper, I guess it would potentially be in your exam. Although there's a lot of things from the paper that we're seeing in this exercise. So it makes sense that if you understand the paper, you would understand here. But if you look at this map, you should be able to interpret this. On each separate year, we have this range of mean standardized yield, which is as a percentage of the median. Notice this is not pounds per acre. It's not pounds of wind per acre. It is a percentage of the median. So it is standardized to that specific year's condition. And so we already interpreted this in previous class, but if you need a refresher, go back to the recording. But basically, you need to know what's going on here and how you would interpret this map. We then check the summaries here to see which years we observed the highest and lowest standardized yield. And then we got into the conversation of how do we do the spatial temporal stability now? So we basically had to first join all those three data sets in a single data set, which right now we're calling SY all. And then after we have three columns for standardized yield for 2017, 2019, and 2020 in the same data frame, we can basically calculate in a row-wise direction the mean across all 3 years and also the CV of all 3 years. And perhaps during the last exercise, I guess you had not read the paper yet, but by today you should probably be able to understand why we're calculating the mean and the CV and how we're going to implement the paper here. Then we made a standardized mean map. And something that I do want to ask you all to see if you're following here with me. So notice that I specifically, on the scale field varieties, I specifically had these breaks of 80 and 120. And on the CV map, I specifically had one break of 30. Why do you think that I made those choices?
Which is like which we call like unstable.
Okay, so Amandeep here in Athens said that's because those are the thresholds that were used in the paper. Right? If you go back to the paper, if you go back to your answers, these were the thresholds that the paper was using to determine 4 different stability classes. And the reason why I chose them here was that so we could visualize them in this field and use that in the exercise. Anyone in Tifton had a comment or question? Okay, I don't hear anything, so I'm gonna keep going. So yeah, the reason why I chose 120 and 80 on the mean and 30 on the CV is because those were the thresholds that the paper used. So following that paper, here's how we're going to create this spatial temporal yield stability classification. If you recall from the paper said that if the coefficient of variation is greater than 30%, then that specific pixel is classified as unstable. In this case, it is basically assuming that if CV is more than 30, then it could be because in a given year, it was high yielding. In another year, it was low yielding compared to the median. And therefore, there's no clear pattern. It is unstable. However, if the CV was less than 30, then we had a new set of conditions that we apply here. So if CV is less than 30, so it is not unstable, it is stable. and the mean standardized yield is more than 120% of the mean in the case of the paper, and of the median in our case, we classify that as high yielding and stable. If the CV is less than 30%, however, the standardized yield is between 80% and 120%, then we classify that as medium yield stable. And lastly, if the CV is less than 30%, however, the mean standardized yield is less than 80%, then we call that low yield stable. So these rules come from the paper. I'm not making them up myself. So basically, now our step is to implement what we saw on that paper and what we just talked about here, but in code. So I left you here this chunk with SY all class. We're going to start off with our object that has the mean in the CV. The name of that object is SY underscore all. If I just print that below here, this is that object, right? So we had the standardized yield for 17, for 19, for 20, and then we calculated the mean, and then we calculated the SD, so we could calculate the CV. And now we're going to use these metrics here to create the rules. Okay, so here's my vision. Let me tell you my vision, and then I want to ask for your help to how can we implement this vision. I want to have a column that I'm going to tell the name that we're going to give it, but we're going to have a column here that under this column, for each row in this data set, is going to look into the CV and it's going to look into the mean, and we're going to give those rules, these rules here, we're going to give in code. And then under this column, basically it's going to say if a pixel was unstable or high yield stable, medium yield stable, low yield stable. That's what we want to do here. How would you do that in code? How would you implement that? I'm going to give you a pipe here, and I'll start simple. What function do we need here at this point? Mutate, right? We want a new column. It has to be mutate. Perfect. So here in mutate, I want to call this column, this new column that we're creating, I want to call this ST class, for spatial temporal class. All right. So maybe let me ask someone in Tifton to help me. What would be the next step here? What do we do now?
I'm not sure if I remember correctly, but we put the range of our CV and then the tilde and one number, like 1 for the low, maybe 2 for the medium and 3 for the high.
Okay, nice. So Benedetta, you're thinking in the right direction, and we're gonna need to do that. However, before we do that, we need to call a specific function here. Anyone remembers what is that function? So remember that we used in the past a function that if you have conditions, which is what we have here, you need to have a function, you need to have those conditions that Benedetta was saying inside of this function that we need to put right here. What was that function?
Case when?
Case when, yes. Who was that?
Mohit.
Mohit. Thanks, Mohit. Yes. Case when, right? So case when is the function that we need when we have multiple conditions that we want to list. In this case, we have 4 conditions, right? So that's absolutely right. Thanks, Mohit. So case when, let's break line here just to make it a little bit simpler. So Benedetta, I want to go back to you because you were answering this part. So I'm going to print below SY all so we can see our current column names. So the first condition that we have to give here is for the unstable class. What column here would you use, and how would you write that condition?
I will use a CV pixel.
Okay, so I'm going to type with you, CV underscore pixel.
Yes, and I will put the sign higher than 30%.
Perfect. And then a tilde, and then how do we call?
Then
Sorry, maybe you
I
said.
will call it one. Oh, can we also call it a text?
Yeah, we can
Not
call
just
Mhm.
okay. Then unstable.
Stable. Perfect. That's exactly right. Thanks, Benedetta. All right, so this is our first condition, right? So if CV of that pixel is greater than 30%, then that pixel is classified as stable, or I'm sorry, as unstable. Now let's add our other conditions. And these are going to be just a little bit more complex, not too much, but just a little bit more. So maybe let me ask Polly, how do you think that we would specify the condition for the high yield stable?
I think we can use the same condition. Then the CV greater than 30%.
Okay, so you're saying if CV pixel greater than,
No, for the high stable, it's less than 30%.
perfect. Okay, what about what else?
Tilde, then high stable.
Okay, we could do this. It would run. But I don't think it would give what we want. And the reason for that is because everything that's less than 30% CV is going to be called high stable right now.
We can also add the condition for the standard yield, the mean standardized.
Okay, so where would you change it?
Instead of tilde, we can add the N.
Mhm.
SD pixel.
Okay.
Greater than 100.
Okay. So thanks, Polly. The overall idea is right on. But I think you missed a couple of things here. And let me ask if somebody else can help you. Can somebody identify one thing that maybe Polly missed here?
Instead of 100, we need 120.
So instead of 100, we need 120.
Yes.
Okay. And then Aman had something here. Yes. So the column that we want to apply this second condition is not SD pixel. SD is standard deviation. We want to apply this condition to the mean pixel, right? This is the column that has the mean standardized yield. Yeah, but Polly, thank you for your help. You were on the right path. And thanks for those that also helped to finalize here. So basically, this is what we want to say, right? So if the CV is less than 30 and the mean pixel is greater than 120, then this is classified as high stable. All right, so that's our second condition. We have two more to go. So let me ask somebody else. Now it's going to get even a little bit more complicated than the second time. How do we specify the condition for the medium stable? Let's see. Marco, what do you think?
I would say CV pixel less than 30 and mean pixel less than 120 and mean pixel higher than 80.
Nice. So yeah, Marco got this right on. So just to walk you all through a little bit slowly here. So the condition of the CV pixel remains the same, right? So we're kind of splitting the data into CV pixel more than 30, everything is unstable. If it's, however, less than 30, then we create other conditions for other classes, right? That take into account mean pixel. So it's still CV pixel less than 30 and mean pixel, or actually, Marco, I don't know, maybe I heard wrong or maybe I typed wrong, one of the two. But really less, right?
Mhm.
Yeah, so mean pixel less than 120 and mean pixel more than
Higher than 80.
larger than 8. Perfect. And this would be our medium dash stable. So
Yes.
I just want to walk through a little bit again, now that we have the code in the screen, that so the CV less than 30 is there the same as before, but now because we have an upper and a lower limit of this class, because the medium class is in between 80 and 120% of the median yield, right? So we have a both an upper and a lower limit. We have to specify both of them in that condition. On the high stable one, we only had a lower limit, right? So if it was 120 or greater, regardless of how much greater it could be, it would still be high stable. In the medium stable, we have a lower and an upper limit that we need to specify on the condition. So just a little bit more complex. And now, lastly, we're gonna do our last condition. So Kiathi, how would you do the condition here for the low stable?
CV pixel less than 30 and mean pixel less than 80.
Perfect, absolutely. And then this is our stable. Oops. Nice. Let's see. I may have done something wrong. Oh no, maybe not. All right, so let's run this. So all the conditions were applied. Now if we print sy all class, let's just take a look at a few of them here. So all of these, at least that are showing on my screen, are all medium stable. Let's see, let's just like quickly check if that makes sense. If our conditions worked the way that they should. So for medium stable, CV has to be less than 30. All these CVs here are less than 30, right? They're all between 3 and 5. So, okay, they are stable. And our mean should be between 80 and 100, which all of these here on this column, that at least that we're seeing right now, are, right? So they are between 92 and 100. So they're all in between 80 and 120. So it looks like it worked. You know, if you just keep browsing on your data until you see other classes. So I just found a few low stable here. So let's check these just to make sure. So here the CV is 8 and the mean is 77. So 77 is less than 80. That's why it's low. And it's stable because CV is less than 30, right? And if you were to keep browsing here, you would find other conditions as well. But so right here we have an unstable one, two unstable classes, and basically that happened because CV was higher than 30. And notice that if CV is higher than 30, it does not care what was the yield, what was the mean yield. It just looks at that CV and then finds that for us. All right, any questions about this in specific? Notice how we basically, you know, and I hope that you're getting this idea that sometimes you may find an R package that does exactly what you need, and sometimes you may just have to do the coding yourself. So here we basically took a paper, read the paper, understood the conditions, and are now applying those conditions through code to our own data, right? So that's basically what we did right here. We just took all these conditions which were specifically explained in a paper and then just implemented them in R. All right. So as always, after creating anything that is map related or anything really, even if it's not map related, I always like to visualize it to make sure that the result that we got is what we were expecting. So let's plot all these classes here. You know what? I'm gonna start to rely more and more on you all and give you less the code myself. So if I tell you here that I want to make a map of these classes, how would you do that? What would you type? I can give you all the ggplots. That's pretty much given. What about now? What geom do we need to show this data? So Amandeep here said geom_sf, and that's exactly right. And if you're not sure what it would be, just have to basically check that this object that we're plotting, there is the one that we created above, is an SF object, right? That's how you would know. So geom_sf is what we need. We need to say data equals to. Now, if I want to have the fill of these polygons, of these tiny cells, colored according to the class that we just created, how would you do that here on code? And let me ask Luke.
Well, first, I think you would need an AES function.
Perfect.
And you set fill to ST class.
Awesome. And ST class is just the name of that column that we created, right? Right there. Perfect. Also, well, we can run this and check what will happen. This is what happens. We have some NAs here. Interesting. We shouldn't have any NAs, but let me see. So we have an NA in this data set. Let me just quickly check why. So I'm gonna do a filter where is NA on ST class. Okay, so we actually have a couple of NAs.
NA is on my code.
You also have?
No, I don't have.
You don't have, okay. So maybe you're not gonna have, because I think this is gonna have to do with the yield, which has to do with the boundary, which all of us have a different boundary. But if you have NAs on your plot, like I do, so this is how I would look for them and understand why they're there, because I was not expecting to have NAs here. So I just did a filter that just kept all the rows where is NA, is ST class was true. So I mean, can anyone help me troubleshoot what happened here? Why do I have these NAs here?
The conditions we set for giving ST class names don't include the values 80 and 120 for mean yield.
Perfect. That's exactly right. Thanks, Luke. So to fix that, we could come here and so let's give like here on the high stable, I just want to change what is currently equal to equal to or what is currently greater than, I want to change that to greater than equal to. So just add an equal sign after that. And then let's also do the equal to on the 80 here. So basically doing the equal to on the lower boundary of the conditions. We don't want to have the equal here as well on the 120 because we already have an equal there, right? So we just want the equal on one of the times where that specific threshold appears. Yeah, I think that should cover us because we have the greater than equal to here, we have the greater than equal to here, and those are the only two thresholds. So if we run that now, at least on my side, I rerun it, and now I plot it, there should not be any NAs. And if I want to check again with the code that I just created here, this should return no rows because there's no NAs. Awesome. Okay, so I'm gonna delete that piece of code. This was my personal checking. And now, so one thing that we've been doing with these plots were to come here on the geom_sf outside of AES and say color equals NA uppercase, because that just removes the outer color of each one of the cells. So it's a little bit easier for us to see. All right, so the next thing I want to do here is change to a Verities color scale. Because we're changing the fill in the AES, because of that, we're gonna use scale underscore fill. If we were changing the color on the AES, it would be scale color instead. Remember that. So scale fill Verities D for discrete, because our classes are discrete values. And I wanna change for the option equals C. So remember that Verities has options going from A to F, I believe, or maybe G, where each one of them is a different color scale. I want the option C. Okay, so this is a map of our stability classes. Spatial temporal stability classes for 3 years of yield data for this one field. And all those years were cotton, but they did not necessarily have to be all the same crop because we are standardizing. So standardization would have taken care of that. All right, so how would you interpret this, Kathy?
We can say that the lot of the field is medium stable. And like we saw, the gully areas, the eroded areas are low stable or unstable. And we also have very less high stable areas. I don't know why.
Perfect. That's exactly right. Thank you so much for that. So I do expect you all to be able to look at a map that we create and interpret. That's probably going to be some questions on your exam related to that. So make sure that you're able to interpret what you create and what we're doing in class. If you're not, let me know and I can walk you through that. We can work on it together. But we need to have that interpretability behind what we make. All right, so just maybe something that's kind of interesting to think about here is the paper created or provided these thresholds of CV 30 and then the 80 and 120 on the yield as our thresholds, right? And we just implemented that. Something for you to be aware as you may be working on your research, or maybe after you graduate from UGA, you may be working with your monitor data. Those thresholds of 30% and 80 and 120% that the paper provides are a guideline, but we also should be aware that to some extent they're subjective, right? There's nothing, I mean, I don't think there's anything special about those numbers other than the fact that they make sense. But it has happened to me in the past that I'm working with your data for a field and maybe none of the data points are greater than 120% of the median. Does that mean the field is low yielding? Probably not. I mean, that's not, I guess, what we should get from it. So what I'm trying to say is if you decide to change these thresholds, so let's say you work on a field where nothing has a CV more than 30%. Maybe you want to stick with these thresholds, maybe not. To some extent, they are, subjective. There is no hard rule to say that these should be the thresholds of these breaks. So for example, if we were to change our CV, well, let me ask you all this, and then we can try out. So right now we see that the unstable areas, as Kathy was saying, so those are the yellow areas. We see there are some here on those eroded parts of the field. We see there are some like scattered throughout, but most of the time they're near the low stable. So let's say that I were to come here and change this threshold. Instead of using 30, maybe I want to use 15, half of that. So if I do that change to all the CV conditions here, change all of them to 15 and keep my yield mean pixel thresholds the same, what is going to happen with the map? Do you think we're going to have more or less unstable pixels? Any guesses?
Unstable.
Sorry, I couldn't hear.
We would have more unstable pixels.
It'll be more unstable pixels, right? Because now we're decreasing the threshold that a pixel has to have in order for it to be unstable. So if you were to run this and then plot it, I mean, of course, it's a visual assessment, so perhaps it's gonna be difficult to really tell, or maybe not. I guess it was not that difficult to tell. We have a lot more unstable pixels, right? So I guess I still want us to use 30 because we have a reference that we can cite for that decision. But I also wanted to make you aware that these thresholds, there's nothing special about them other than that they make sense, right? They could be higher, they could be lower. It's just up to perhaps your own data set. Sometimes you may have a data set that has no CV more than 30. Then what do? Do you keep this or do you choose one that makes more sense to you? I guess it's going to be up to you, but I just wanted to help you think in that way as well. All right, so I just returned to my 30% threshold. So just to come back to where we were. All right, so now we plotted it. It makes sense, right? We're seeing that low stable and unstable are all near the parts of the field that were eroded. Maybe except for that one on the top right there, that I actually don't know what's going on with that area. But overall, it makes sense, right? I mean, at least I thought that we would have more high stable on the left side here. We don't have a lot, but we have a few. And one question that you may have here is, for example, what proportion of all the pixels on this field, what proportion falls within each one of these classes? I guess just visually, we would imagine that medium is probably the highest proportion. But is it 60%? Is it 80%? Is it 90%? I guess my eyes and brain are not good enough to do that approximation here. So let's calculate that. Let's calculate what is the proportion of each one of these classes within this field. So we're going to start off with this object SY all class, right? That's the one that has the ST class. And so we have not done this in this class, I don't think. But maybe, and I'm not going to probe you too much, but maybe it's, as we're walking through this, maybe try to check in with yourself and see, could I have guessed those steps? Would those make sense given what I already know on how to do this? So imagine that now the goal is to have a column that's going to say what percentage of this field is covered by each one of these classes. Because I want to calculate something according to each class, so the proportion of each class in the whole field, I need a group by. So let's group by ST class. And now, for us to calculate the proportion of pixels of each class within the whole field, we need two pieces of information. What are they?
The total number of rows.
That's one. What's the other? Okay, yield, but that's not, so we don't need to know yield to know the proportion of pixels within each class, right?
Number of rows in each class.
Yes. So Marco said total number, I think it was Marco. Was that Marco?
Yeah.
Marco
Yes.
said total number of rows and Kiathi said the number of rows in each class. Yes, those are the two things we need to know to calculate the proportion, right? So there's a couple different ways of getting the number of rows in each class, but the easiest one is a function called tally. So because we group by and then we ask for a tally, it's gonna tell us what is the n in each one. So it's basically the number of rows within each one of those classes. So now we know how many cells are within each one of the classes. Now we need to know the total number of cells across the whole field. There's a couple ways we could have done that. So one, if it's simple enough, you could have just print SY all class and realize that at least on my side, I have 4,046. That would be a very manual way of doing this. We can do another way as well. So before we do the group by, we can come here and create a mutate. I want to call this uppercase N, meaning that is the number of total observations. And this is basically just, there's even a couple of functions. Let's try N row first. N row and give it a dot. Let's see if that works. Okay, so I think it worked. And then we have this column for uppercase N. So this is just returning the total number of rows of our data frame. But notice, even though this number is the same all the way down on this data set, it's all the cells are the same. On my side, it's 4,046. On your side, it's going to be a little bit different because of the grid and because of the boundary. But it's going to be, nonetheless, the same value all the way down. Notice that I use a mutate instead of a summarize. If I ask a mutate, it will calculate whatever I'm asking, but it's not going to decrease the number of rows to summarize by a given class or a given column, because that's not what I asked. So it just created that column and repeated the same value all the way down. Now, if we plug that into this group by, and we'll let it go like that, what happens is any variable that is not in the group by is left behind. So we lost that uppercase N that we calculated before. A way that you can keep that is just by including that column on your group by. So if we do this, you keep that column that does not necessarily set any group, but it's a column you want to keep after you do the tally, which the tally is just to summarize getting the length of the rows within each group. All right, so now we have lowercase n, which is the number of cells in each one of the classes, and we have uppercase N, which is the same for everything because it's the total number of rows for the entire field, not within any given class. Now, how can we calculate the percentage? Okay, so let's begin with the function first. What function do we need here? Anyone in Tifton can help me guess what is the function we need here to start calculating the proportion?
What about mutate?
Yes, thanks, Polly. Mutate, right? Because we just want to create a new column. I want to call that prop, just so we all have the same name. Now, what do we need to do here to calculate the proportion? What would you type here for that?
I'll type the normal formula.
Which is?
So I know for the percentage, if it's for the highest table, I'll take that the number of columns in the highest table divided by the total n. That will be n over n small over n capital, then times 100. Bracket, yeah, okay.
So at least on my side, it did calculate, but it's on that column. That's exactly right, Polly. Thank you. Yes, so we just want how many rows we have in each class divided by the total number of rows, which is the same across this column, and then times 100. That's exactly it. So then we know here that 84% of our field was medium stable. Oh, I just noticed I made a mistake on when I created the class. So let me just come back here. Medium stable. Right, so we have 84% in medium stable, and then we have about 10% on low stable, and just about 3% on each one of high stable and unstable. So those would be our proportions. Perfect. All right. Any questions about the code or maybe the actual classes? All right. I don't hear anything. So let's go ahead and so now we finished this exercise, which the goal of it was to create the spatial temporal stability classes just like in the paper. So that's it. This is it, right? Now we're gonna see this again in a future exercise. And because of that, I want to export this layer here to file so we can bring back again in a future exercise that we're gonna validate these zones. So with that, we need to export it. What function do we need here again? WriteSF, right? So that's what Amandeep was saying here. So WriteSF is the function we need to write this object to file. So the object name again is sy_all_class. And then we give it a comma, we give the path, the file name, and the file extension. I want to get outside of code, go inside of data, and then export this as sy_all, that's the file name. And then we give it the extension, which for this class, we're gonna use GeoJSON. Also, we always, every time we use WriteSF, we want to change the behavior of the argument delete DSN. We want to say delete_DSN equals the true instead of the default, which is false. We run this, and now you check on your data folder. It should have the sy_all.geojson file right there. Okay, so a very quick summary here is on this exercise, we imported all the three. So remember that what we imported was the wrangled, clean, and interpolated versions of each year of yield data that we had for 2017, 2019, and 2020. We then, within each one of those years, we extracted the median value of yield and standardized everything else to the median, in a way that our range of values would be centered around 100, but we would have values more than 100, values less than 100 within each one of the years. Now, when we have the standardized yield within each one of the years, we join all of them into one data frame, and then we calculated for each one of the cells the mean standardized yield and the coefficient of variation of the yield across those 3 years. And then finally use the mean and the CV to apply the rules that we learned in the paper and create the stability classes for this case. Okay, any questions about what we just did? All right, I don't hear any. So, you know, I would talk about assignment 7 if we had not yet done it, but you already did it, you already submitted, so it's already in. We don't have to talk much more about that at this point. So that wraps up our yield exercise. What I want to do here before I let you catch a break is let's set up for the next exercise. So make sure that you save your script, and once you save your script, feel free to just close RStudio. I want you to come back to the main folder of the class, and we're going to start a new exercise today that is called terrain. So I want you to come here and create a new folder that's called 08_terrain. you can come in this folder, create your subfolders of data, code, and output. Before we create our RStudio project, I just pushed a new script, a new partial script to GitHub today. So you can go ahead and, oh, you know what? So before you pull GitHub, give me just a second, because I pushed the script, but I did not push the data file. So let me push the data file, and then you can download both of them. So let me do that quickly here. So now I'm gonna push this, and then you should be good. Okay, so now you should have on GitHub both the new data frame and also the new script. So make sure you download that, and you already know what to do. You just need to move the new data file, which is called 08 elevation. To the 08 terrain data folder. And from 04 class code on GitHub, we have a 0225 terrain partial script. You're gonna copy that into the code folder of 08 terrain. And once you've done that, I'll ask you to create a new RStudio project inside of 08 terrain. Right, so this workflow is something we've always been doing in this class. It's probably the 8th time we do it. So I do expect you to be familiar with it, and how, if I just ask you for you to do it, you should be able to do it on your side. So I launched RStudio. Regardless if you're in a project or not, I'm gonna click on new project. And then existing directory, because we already created it. We want to browse to the 08 terrain. And once you are inside 08 terrain, you click open, create project. And that would have us set up to do the next exercise. So once you are,
Can you we can find the data, because on
Yeah,
my file I don't have the data for the
same.
terrain.
I think the data is missing.
let me check on GitHub. Maybe I missed something. So the data is under 03 data. It's that 08 elevation.csv. So it is on GitHub. If you don't have on your computer, then maybe you don't have the latest GitHub version.
I'm gonna download it again.
Okay.
Okay, now it's there.
Perfect. All right, so with that, and with the 08 terrain project created, we're just gonna launch that. We'll go on the code subfolder and launch that partial code. And this would be our starting point for the next 40 minutes, but I want to give you a break. So let me set a timer here for 5 minutes, and then you can catch a break, and when we're back, we're going to start working on this project. All right. Right, so let's resume here. Okay, so I'm assuming you were all able to get to this point with all the files in the right place and create the RStudio project. If you were not, let me know. But if I don't hear anything, that's my assumption. Okay, so let me kind of paint a picture of what we're looking ahead. So we have yield data from 3 years. We process that data, right? So we did the wrangling, we did the cleaning, we did the interpolation, and then we combine all those interpolated, clean, wrangled yield data into one object to do the spatial temporal analysis, which is what we just finished. So now we know what parts of this field, are have different characteristics as far as stability, spatial and temporal stability of yield. That's a really important information for us. And however, if you think about it, we know how yield is responding in this field, but we don't know yet why. We don't know yet what's the cause of it. Is it something that we can manage? Or is it something that perhaps is not manageable? So, one thing that happens a lot of times in precision ag in these types of cases is, so you know where yield is and how it behaves in your field. Now the next question becomes, why is it that way, right? Especially where you don't have high stable yield. So that part, maybe you don't have to address much else there. But maybe why are your low areas low? Why are your medium areas medium? And especially, why are your unstable areas unstable? Because unstable of all these classes is the most uncertain, right? Because maybe this coming growing season, that unstable area may be high yielding, depending on weather, for example, and how weather interacts with your soil, with your terrain properties, with your just overall management. So if your unstable area this year is high yielding, you may decide to apply more inputs. But maybe next year is going to be a low yielding, is going to be unstable because it's low yielding. So then maybe you decide to apply less inputs instead. But because it is unstable, and at least at this point we don't know why, it's hard to really use that information for management purposes. So we are at this spot where we know what parts of the field behave differently in yield, both spatially and temporally. Now the next step is going to be for us to bring other types of information about this field that may help us understand the why behind it. So why are those areas that way? And that will help us to think about, well, if the reason why something is low yielding, if that reason for it to be low yielding is manageable, let's say, oh, maybe the pH is too low. We can apply lime and increase the pH to a better value range of pH for a given crop. Or maybe a given nutrient is lacking. Maybe it's too low on phosphorus or potassium. All these are manageable, right? We can manage for improving those low yield to perhaps medium, perhaps even high yield. But what if that is unmanageable? What if your low yield values are because they are in a low-lying area of the field where a lot of water accumulates, it has waterlogging issues that basically kills plants, and you have a low stand of plants on that part of the field? Maybe, I mean, it's still manageable if you use drainage as an option here, but overall is a little bit harder to manage compared to a nutrient or pH, right? So there are things that we can manage for the better. There are things that may be unmanageable, but it's still important to know, because if it is unmanageable and you're always getting low yields out of that part of the field, you may decide to not even plant that part of the field anymore. If you keep consistently getting low yields and potentially getting a negative return on investment, right? So this exercise today and the ones that will follow probably for the next few classes is going to be us bringing other pieces of information about this field and try to understand if they can help us put a reason behind these classes, these stable and EO stability and EO classes that we just created. Today, we're going to start off with elevation. As you know already, you already pulled elevation from open source data sets that are available, right? We did that for the exercise that you use your own field boundary for an area that was of your interest. In this case, we're going to be using elevation data that is not open source. It's basically a proprietary elevation data that was most likely collected when a tractor with RTK was moving through this field, maybe planting, or maybe doing soil preparation, soil cultivation, whatever it is. Every time a tractor or an implement that has GPS, especially RTK, once that equipment goes through your field, is going to be collecting the location data, but also the elevation data that we can use to learn about elevation of this field. So today, again, we're going to be using a proprietary elevation data from this field to learn more about the terrain properties of this field. So the specific objectives here are going to be to import a point vector layer of elevation. Because it is a point layer, we have to interpolate it. So we're going to interpolate that and have a continuous layer of information that initially will be a raster, but we're going to transform that to vector, as that's what we're going to be doing for all layers in this class. While elevation is still in the raster format, we're going to use that to calculate secondary terrain variables, which are slope, aspect, and flow direction. And once we do all that, we're going to then export these terrain soil layers to file. So something that you're going to realize in this exercise, and I just want to say this one more time, just to help you to incorporate that knowledge, is elevation is the primary terrain layer that we're bringing here. Elevation is the primary layer that we're bringing here as it relates to terrain. Then elevation is then going to be used to calculate secondary terrain variables like slope, aspect, flow direction. There are other things that I guess this exercise does not incorporate, but we could calculate, like the topographical, TPI, topographical position index. There are other indices related to water movement. We can all calculate those secondary layers based on elevation, which is our primary layer for terrain properties. So that's what we're going to be doing this exercise. I left you all the packages we're going to be loading today, so you can just go ahead and play that chunk. I think you have all of them, so you shouldn't have any issues. I'm creating here a default map theme. So what I want you to notice is that is using the theme map, which is a theme that we've been using in ggplot. And I just am creating I then call the function theme alone, and then change some of the defaults related to theme map. So I'm changing here, for example, to have the legend on the right. I'm changing here the way that the panel and the plot looks like. I want them to be gray. And then changing the size of the legend title and legend text as well. And I'm assigning all those changes to an object that I'm calling myTheme_map. With this, whenever we make ggplot maps in this script, I can just call myThemeMap, and that's going to apply all these changes to that plot without me having to type all of them over and over again. So make sure you run that so we have the myThemeMap available on your environment. All right, so the first thing here is going to be to import the data. So the data that we have is this one. This is what we have on file. What function do we need to import this data? Yeah, I heard I'm saying something here. Let me see if somebody online can help me figure out.
read CSV.
Read CSV, right? And the reason why we know that is because it is a CSV file. So let's go ahead and do a read underscore CSV. We're going to specify the path to that file. So we need to get outside of code, inside of data, and then call that elevation.csv. If you run it, you get some messages there, but there's nothing to worry about. And then you can print it just to check what it is. So a quick inspection here. We have, about 55,000 rows of data in this data frame in 5 columns. We have here, really object ID and point ID are just IDs, which are not very useful for us. This column here called grid code is the column that actually has the elevation, and this is in feet. And then we have point X and point Y in WGS 84. So as I hope you're already thinking, we're gonna have to do some wrangling here to get this to the stage that we need to be able to use as a geospatial file, right? So right now, this is just a data frame. If you do class of elev, this is just a data frame. It's not a geospatial object. So we're gonna have to do some wrangling here. And I will rely solely on you to do this. So we're going to start off with elev, which is our initial data set. I'm just going to print elev below so you can see what it is. This is what it is. Okay, so I'm going to ask each of you to help me with different points of this wrangling pipe flow. There's going to be a few, well, more than a few, but a handful of steps that we're going to have to do here on this ring. And although some of them may not really matter the order, but others will. Like, we will have to do some things before other things. So maybe before we think on the geospatial aspect, before we get to that aspect of the wrangling, what would you do on this data frame that you're seeing printed below here as far as wrangling is concerned? Okay, so Amandeep said clean names. This is not like an extremely required step, but I always do this just so it makes my life easier when I need to refer to them. So if we do a clean names and then we print it, now our column names are a little bit easier to know. Perfect. Thanks, Aman. All right, so maybe let me go to Tifton and check with you with all of you in Tifton. What would be the next step that you would do here on your wrangling pipe flow?
ST as SF.
Okay, so Benedetta said ST as SF. I totally agree with that. And that will be a step here. There are a couple of things before we get to the geospatial side that I would like to do here. So maybe I'm going to tell you, and then you can tell me how you do it. We can think about it together, but that's definitely right, Benedetta. At some point, we're going to do exactly what you said. So, well, let me tell you here that the elevation is on this column called grid code, and it is in feet. So I guess one thing that I dislike is the fact that this column name, as it came to us, is very uninformative and it has no units. Right? So perhaps the first thing that I would like to do here is to rename this column to actually say what it is and include the units of measure that it has currently on that name. So how would you do that? Mutate. So maybe let's call this elev_ft for feet. Or I mean, sorry, was that what you were thinking, or were you going in a different direction?
It says, then you take the name of the column and equals to.
Mhm.
And the name of the color, that is object ID or point ID.
So the object ID and point ID are actually not very useful. So let me maybe help you out just a little bit here. So there are different ways that we can rename objects. We can use this dplyr select to rename, or we can use a function called rename as well. Maybe I want to rename here first, and I want to say elevation elev_ft equals to grid code, just so we get the column with its appropriate name and there's no confusion from this point on. So we basically just changed the name to elevation in feet. Now, you know, another step that it may not be required, so maybe you're not thinking about it, but it's something I want to propose that we do, is to transform this to metric system. Right now we have in feet, but maybe I want to create elevation in meters instead. So I'm gonna give you the conversion factor, so we all have the same. If you did not, I mean, I don't know that conversion factor from memory. Why would we? But if you need it, you know, you just Google it and you would find it. But basically, it is times 0.3048 is the conversion factor. But then we have to say something here before this asterisk. What are we missing there? Elevation.
Level
11 feet.
Yes, perfect. So this is our conversion from feet to meters. We can run that and then print. And okay, so it's starting to look better, I guess. One thing that I want to do here as well is I want to select just the columns that we really need to move forward. So I want to give a pipe. I want to call dplyr colon select. What columns do we really need here moving forward, in your opinion? What do you think, Yaffi?
LF meters, point X and point Y.
Perfect. 11 meters, point X and point Y. I agree with that. Point X, point Y. All right. Now, I guess we've done the wrangling on the data aspect of it. Now we're ready to work on the geospatial side of it, which is what Benedetta was saying earlier. So Benedetta, can you remind me what you said earlier?
ST as a set.
Okay. So here we're transforming this from a data frame to a vector, right? And then we need to change something here, or we need to add something else to this function.
The CRS.
Sorry, can you say that again?
The CRS.
Okay, so I think we're missing one step before that. So let's just try to run this way. Okay, so it says no simple features geometry column present. So I mean, the error is not very helpful, but I don't know if you were able to get what's going on here.
Yeah, maybe we have to put the coordinates like X and Y.
Yes, that's exactly it. So Benedetta said that, and Amandeep also mentioned that here. So we need to specify the coords, use the C function, and then give in quotation marks point X and point Y. Awesome. So now this is an SF object, right? Let me see here. Marco, what do you think would be the next step now?
I think it's fine. Now we can set the CRS.
Yes, set the CRS, right? Because as you were seeing here, CRS is NA. So we have to set the CRS. Do you remember the function for that?
Yes, st underscore set underscore CRS.
Awesome. And then here it has an argument for a value. So this is where we give the EPSG code for WGS84, which the code is 4326. So if we run this, and then we printed, now we have WGS84 as our geodetic CRS. Okay, is that all? Or do we still maybe have something to do here? Okay, so Amandeep is saying that we need to transform this to UTM, right? Why do you think that we need to do that? No, I mean, why do you think that we have to transform?
Because, for the like bigger.
Yeah, so 4326 is WGS84, which is a geographic CRS, right? But then you said we want to transform to a projected CRS. And then my question to you, and maybe all of you, if you're thinking about it, why is that? Why do we have to do that step? Yeah. Well, let me see if somebody can help you. Anyone online? I mean, maybe you can disagree with Amandeep. Maybe you can say that you think we don't need to transform, but then I'll also ask you why. So right now we are on the question of Amandeep suggested that we do the ST transform to change the CRS to a projected CRS, and then I asked her, well, okay, why do you think we need to do that? Can somebody help either to defend her opinion or to argue against it?
I don't know if this is correct, but projected CRS is preferred when we are dealing with local fields because it's really small and they're accurate. Maybe that's why.
Yeah, that's a good, it's definitely true what you said, Kiathi. Also, so really the key thing that I want you all to realize is we want to transform this to projected because we're going to be using distance-based operations like interpolation. So we're going to be interpolating these points here, and that is a distance-based operation, and therefore we want to have him projected. So Aman, you were correct, but I was just trying to see if you're going to tell me the why of it. Yeah. Yeah, this is in meters for sure. Awesome. So Amandeep was saying to use the function st transform. Here we have this argument for CRS, and the value that we want to use for this field is 6345. So if we run that and then we print it, now it is a projected CRS UTM zone 16 north, which is where this field here is. All right. So next is I want to do some EDA as always, right? We always do EDA to check our data. If you just run the code I left you there, this is what you're going to see. Before we talk about the actual visual, the actual map, I want you to come back to the code, delete those 3 dots and comment, add a plus to the end of that line right there, and let's call our object that we created before for the theme, which is called my theme map. So remember that we created on the first chunk of the script a theme for us. So we're just calling that right here. And then this is how that looks like. All right, so I guess a couple of different ways that we can talk about this map. The first one of them that I want to invite you to talk about is basically what we are seeing here in this map. So how would you interpret this map here? Let me see, let me ask Luke. How would you interpret this map?
Sorry, you're muted. The west side is on average a little bit higher in elevation, and I can kind of see a little bit that some of these like the channels that we were seeing of erosion are kind of like, you can see little tendril shapes where they're lower elevation, they're kind of cutting into these small hills we have. And I guess just like in absolute terms, the difference in elevation is of like 6 meters at maximum, like across the whole field, around 6 meters.
Perfect. Yes, that's exactly right. Thanks, Luke. Yeah, so Luke made mention here that we can really see now what we were already seeing on EOD, already seeing on the satellite base map of MapView, the fact that the eroded parts of the field are also showing up on the elevation as lower elevation, which makes sense, right? If you are eroding soil, you're losing that soil away with water, and therefore you're leaving behind this gully that is going to be a dip on your field pretty much. So we can really see those. We see the highest areas in yellow, right? So we see like that maybe this middle top part of the field is a little bit higher. And then we have this gradient to both sides, but the gradient is more, has higher magnitude as you move to the right. Perfect. So, something I was just wondering here is, I thought if we print LFW by itself without being part of a plot, I thought this was a point SF. But then when we make this plot here, it looks like we have some polygons. It looks like doesn't look like it's points. What's going on here?
Maybe it's continuous.
So what's happening is just that we don't have, we have a lot of points. So they're just overlaying each other. So one way that we could just, because we have like 55,000 points on this data set for this field. So one way that we could just play around a little bit and have an idea of if that's actually true or not, at least visually, there's a function called simple frac from dplyr that you basically just say the size in a proportion. And this is, so if we say 0.5 is going to take a random sample of 50% of the rows of the original data set. So if we just run until this point before giving a pipe at the end, we just see that we get about half of the rows, and it's just a random sample of those rows. So if I plug this into ggplot with just half of the points, we start seeing some holes now, right? So it's just one way that we could have to check if this is actually what's going on here. It's just that we have so many points across this field that it looks continuous, but it's still a point object.
Dr. Bastos, can you please go back to EDA? I think I missed something.
You mean this chunk here?
No, the LFW, where we did the ST transform. Yeah. Okay, thank you.
Yep.
Mhm.
All right. Great. So we brought our elevation. We've made some visualizations to check for it. Now we're going to interpolate, right? So we're going to do the same thing that we did for yield, but now for elevation. If you remember, and it's important you do remember this, to do interpolation, regardless of the algorithm, you have to have a grid. You have to have a grid over which you will interpolate each one of the cells. So if I ask you to create a grid, you should remember that we need a cookie cutter first. We need to know a grid over what. Where is this grid going to be located? And that we use the boundary for that. We use our boundary to be our cookie cutter for the grid that will be created. So with that, we're going to first have to bring our boundary here. So if you remember, the boundary is not in this project, it's in another project. So we're going to use readsf because the boundary is an SF object. And then we're going to navigate to first outside the code folder, then outside of 08 terrain. The boundary is going to be inside 05 digitizing, inside the output subfolder, and it's going to be your boundary.geojson. That's where you should have saved your boundary when you did digitize it on that exercise. So if you run it and you print it, so the boundary is already an SF object. However, it is in WGS 84. Remember that we always want to have all of our objects in a given analysis using the same CRS, so they all line up perfectly. So we have to do a very quick wrangling, which is going to happen right here. We're not going to have a full chunk for it. So just add a pipe. We're going to do ST transform and then do a CRS equals to 6345. So we transform this from geographic to projected. So now our boundary is on the same CRS as our elevation data. Okay, so now that we have our boundary, we can go ahead and create our grid. So we're going to create this object here, grid_r. We've done everything we're going to do next. We've done exactly like this in the previous interpolation scripts. So this next chunk, you're already familiar with it. You may not remember from memory, or you may not be able to recall from memory all the functions, but you've done this 3 times at least. So we're going to start off with our boundary. That's our starting point, our cookie cutter. Let's give it a pipe. Does anyone remember at least the name of the function that we need here to create a grid?
Set grid.
ST make grid, right? Thanks, Polly. Thanks, Aman. So here we specify our cell size is going to be equals to 10. Remember, this number here is in the units of whatever is the CRS you're using for the cookie cutter boundary. If boundary is in degrees, this is 10 degrees. If boundary is in UTM zone 60 north, this is 10 meters. So remember that. So the process here, after you run that, the process involves piping this into an ST as SF, just to force it to be an SF object from that point on. And then with this, if you just print grid R, we have at least I have 6,048 rows or features in 0 fields, because we basically just have the geometry field, which doesn't count as a field. And this is SF. So this is a vector layer. Remember that to actually do, so I want to just bring your attention here for a second that we create the grid initially as a vector because the function is based on vector. We then transform that to raster because the interpolation function requires a grid in raster. So we give the grid as a raster to interpolation. And once we get the interpolated points, so we transform back to vector because that's the format we're using for this class. So we're going back and forth between vector and raster a couple times. I just want you to realize the why and when we do each one of them. So right now the grid is vector and the interpolation function requires a grid in raster. So we have to rasterize this grid that is currently a vector. So for that, we're going to use a function st_rasterize. That's the function that actually does the rasterization. So from vector to raster. And it has a couple of arguments we want to change. One of them is dx. That's the distance on the x-axis. That's the pixel size of this grid. We just want to keep dx and dy equals to 10. And if we run this and you print grid R, now grid R is a stars object, which if you remember, and I hope you do, because this is definitely going to be a question in your exam, stars object is a raster object. And an SF object is a vector object. Make sure you know your packages because we've used these a lot. if we just do a very quick plot here, just to visualize this boundary, you can keep that ggplot that I gave you there, add a plus. So if I want to plot this object, grid R, what geom do I need here? Okay, I'm on DP saying geom stars. Does anyone disagree with her? Okay, I don't hear anything, so I guess everyone agree with you, Aman. And that's probably because you're right. We need geom stars. So geom stars is what we need because this is a stars object, right? Grid R is a stars object, so we need geom stars. So we just say here data equals grid underscore R. And I just want to add the object my theme map just to keep consistency. So if you run that, this is what we see. It's really not very useful at this point, or at least it's useful, but not for our understanding of it. One thing that's happening here is that the grid, if you remember, a raster object has to be a continuous object within a bounding box. So there are cells everywhere inside of the bounding box, which is, in this case, the bounding box is set by our boundary. But I do not want to interpolate outside of my boundary. I want to first use my cookie cutter of boundary to clip or crop this raster and only keep the cells inside of the boundary. So we come back here to our grid R, add a pipe, and we're gonna call a function stcrop. Okay, that's it. stcrop and then give the boundary. So boundary W. So if we do that, and then we plot it, now we should see kind of our field. Remember, if you remember, geom stars does not use a fixed coordinate axis on X and Y. That's why it looks a little bit distorted, but it is our field. And it is only the cells that remain are the ones inside the boundary. Again, notice that outside of the boundary, those cells did not disappear. They're just set to an A. They all became an A outside of the boundary, but the cells are still there. And that's a key difference between raster and vector. Raster has to be a continuous in a rectangle format given your bounding box. A vector does not. You can have a vector of a point and it may just be a single point, and that's it. It does not need continuity, whereas raster has to be continuous. Okay, I think this is a good point for us to stop. We just have another minute here, so save your script. You can close our studio. I will take your attendance very quickly here. And before you go, I have a quick reminder for you about the midterm. All right, so claim your attendance. And before you go, I just want to remind you the midterm is going to be next week. You're going to have to come to your own campus location. If you just show up on Zoom, not on your own campus location, you're not going to be able, I'm not going to allow you to take your exam. So make sure you're on campus, on your computer lab. You will also not be able to use your computer. It's going to be closed book, and you're going to do your exam directly on the computer of the computer lab. So the desktop in front of you, if you are in the computer lab, which you should be there. Otherwise, I will not allow you to take the exam. So make sure you are in your computer lab. Make sure if you want to bring your laptop, I mean, there's nothing keeping you from that, but you're not going to be able to use it. You're not going to be able to open it. It's only you and the desktop in the computer lab. And the exam would be through ELC. We're going to have a series of questions that are going to be multiple choice, short answers, mix and match, fill in the blanks, all those things. You will be asked things about code. You don't have to, again, remember code completely from memory, but I may ask you, what function would you use to bring a given data frame? Fill in the blank on this ggplot code to make sure that the output looks like this. Things like that. So be familiar with your code. That is sufficient. any quiz, any assignment, any reading assignment, any lecture, any notes that we have in the actual scripts, those are all fair game. And yeah, and really let's include until the yield stability that we finished today. I think that's a really good stopping point, and it's not a lot more than what we had done until last Thursday. So let's include until the end of yield stability that we finished today. All right, that's all I had. Any questions for me? All right, I don't hear any, so I'll see you on Thursday. You're gonna have 2 hours for your exam. So bring water, bring maybe some snacks, and yeah, let us know if you need any help in the meantime.
Thank you.
All right, thanks everyone.
Thank you.
Thank you.